So, part A of this lab experiment was very long-winded. I know that. It was probably one of my longer videos that I've ever recorded. It was over an hour. But imagine you only had to sit there and watch that video for an hour. You put me on double speed. If you put me on double speed, you were just there for 30 minutes. And imagine the time that it would take if you were actually in the lab to do it in person. So I just did you a favor with an hour video, didn't I? Otherwise, you could have been in there for 2 hours, 3 hours, or even longer, depending on how particular you were with your lab technique. All right, so part B of this lab experiment is going to concern density of an unknown. So this actually had nothing to do with the first part. This is just an addition that they decided to squeeze in instead of making it a separate lab experiment on its own. So density is another one of those common laboratory techniques that we always have to do in a lab. It seems like we're doing it all the time. And this is just a training exercise on how to do density a number of different ways. That's what this is all about. Okay, so in the beginning of this lab experiment, they are going to tell me that I need to double check my technique before I do anything else at all with the unknown that they have provided me in the lab. So how do I double check my technique? Okay, so this is what they're telling me to do. So the directions are going to tell me to go to my balance. So here's my balance, and to take a container. They call it like a dram cap container. Okay, well, whatever. Any container will do. It doesn't have to have a lid. The things that I'm using, they don't evaporate off very easily, so they're going to stay behind. I don't necessarily need a lid for that. If it was something that did evaporate off easily, then I would have to use a lid, so that way all of the sample will be trapped and contained in the container, which is why we call it a container, people. All right, so here's the balance. Here is my empty container on top of that balance, and I have tared that balance. So 0.0000 gram. There it is. All right. So there's my empty container. And then it tells me to take like 1.1 milliliters and add it to the container. Whatever. We're not doing that. I'm going to modify this laboratory procedure. And we can do that if we're allowed to do it sometimes, as long as we make notes of what we did. No big deal at all. So instead of using volumetric pipettes and graduated cylinders, which are not accurate, beakers, which are not accurate, volumetric pipettes would be accurate, but volumetric pipettes tend to be very, very finicky if you're not used to them. I decided to make this process a little bit quicker and a little bit more relevant. And the way that I did this is to use what we call a micropipette or a micropipetter. Some people in biology world also call these pipettemans. All right, so this is a micropipetter, and on the front of the micropipetter, you see the stamp at which it is suited volume-wise. And it says 100 to 1,000 microliters. All right, so we've got to kind of hone in on that first. We got to feel comfortable with that. So 100 to 1,000 microliters. All right, that's not milliliter, people. That's microliter. Microliter and milliliter are related. They're different prefixes, though. I'm going to give you the short-handed version of this just because it's not general chemistry, it's not dimensional analysis, it's not shifting a decimal back and forth. I mean, that kind of stuff can be taken care of in a different class. The easiest way for us in a lab to go from milliliter to microliter is to move the decimal 3 times. All right, so what that means is that 100 microliters is actually 0.1 milliliters. There's 3 zeros or 3 placeholders, magnitudes, that are different between those two numbers. So 500 microliters is actually going to be 0.5 milliliters, okay? 1,000 microliters is actually 1 milliliter. That's how we read these numbers. So this micropipetter that I'm getting ready to use is suitable of 100 to 1,000 microliters. In other words, 0.1 milliliter all the way to 1 milliliter. that micropipettor is appropriate for that amount. Okay, so in the beginning of this lab procedure, they're telling me to take 1.1 mils of water. Whatever, we're not doing that. We're going to take 1 mil of water. And I'm not going to pipette it. I'm going to use a micropipetter. And I'm only going to pipette 1 milliliter of water into that container. In other words, the dial on my micropipetter has to stay 1,000. Now, if I look at this dial and I look at the numbers up here, it says 100, right? There's a 1, there's a 0, there's a 0. Here's the problem with the micropipetters that we have here. There's only room for 3 numbers. And 1,000 has 4 numbers. So we have to make do. These things are made on a manufacturing line. They are adjusted. They are fine-tuned for different amounts. And the majority of them only have 3 digits. We use these for pretty small amounts of volumes that we need to add. And 1,000 just so happens to have 4 digits and not 3. So what they decided to do is have your 4th digit down here at the bottom that's kind of hidden. In this picture it's hidden, but they're small little tick marks. So when this says 100, that actually means 1000, which is 1,000. So that's why I dialed this to what I did. It says 100 on here, but that 4th digit is somewhat hidden to you right now, and there's small little tick marks down here at the very bottom. That is our 4th digit that we need, okay? Now, if I need it to dial 800, then that means this needs to say 080, and the little tick marks down here at the bottom would also say 0. There is my 800, or 0.8 milliliter. If I needed 100 microliters, or 0.1 mil, then this needs to say 0100. There is my 100. All right, so just a little bit about our weird little micropipetters that we have in the lab. That's how they're made. Some of the more professional micropipetters that could cost $1,000 or more, they do not have this weird ambiguity in place, and they really do have a true proper readout. But these, they're pretty cheap. They're made for student use, actually, and they just thought they could get by with it without a problem. All right, so I dialed this into 1 milliliter, and the way that I use this thing is that I'm going to put the tip of that into my DI water, because that's what they want me to pipette. So the tip is going to go in, but before I put the tip into that water, I want to create an air pocket first. I need to suck that water up into that micropipetter tip. So I have to push down on the plunger up here at the very top. There's actually 2 stops. This plunger pushes down to stop number 1. It's pretty forceful. You know, if I slowly push that plunger down, I'm going to stop right there, and I think that that's probably as far as it can go. But there's actually a second plunger piece that this micropipetter can actually be pushed to a little bit more. So with the plunger, push it down to the first stop, and then I take the tip of the micropipetter and I put it down into the water or the sample that I'm trying to suck up, and then I slowly let up on the plunger. And when I do that, I'm going to see some liquid that gets sucked up into the micropipetter tip. And I can see that liquid layer. It's right there. Okay, so that's if I use this the right way, that should be 1 milliliter, 1,000 microliters, 1 milliliter of solution in my micropipetter tip. So that tip actually holds that volume on the inside for me. That sucking motion sucks it up in there, and it doesn't spit any of it out until I tell it to. So I take this micropipetter tip, and then I put it over to my empty container that's here on the balance, and then I will slowly push down on that plunger yet again. And when I slowly push down on this plunger, I'm going to go to that first stopping point, and the majority of my liquid will be empty. It will be out of the tip. But there could be a little bit of residual that's still left. So the reason that this second void is in there, the reason that that second plunger stop is present, is because this will deliver a little poof of air through my tip. And that poof of air will push out any residual stuff that still might be present in my micropipette tip. So I push it down to the first plunger stop. The majority of my liquid will be gone, and then I push it down a little bit extra, and that will force a little puff of air to go through the tip and push everything out that needs to come out. All right, so here's a video that basically kind of shows you the setup that I'm getting ready to do. So once more, let me turn myself off and turn myself back on. All right, guys, so this is part B of the experiment. Part B of the experiment is going to get you to measure the density of water just to make sure that you can actually use this system the right way. And here you're going to see a bottle of DI water that I'm going to be using. And then after that, they want you to determine the density of an unknown solution. And right here in this container is an unknown liquid for me. And I'm just going to measure that, and I'm going to report the density and try to match that density value up to a list of possible compounds. Well, there's a couple of ways that I can do this, but I'm going to be using what we call a micropipette, and this is what a micropipette looks like. It is a way for me to measure out volumes, and that volume is going to be very specific. This is much easier, it's much quicker, it's better than an old-fashioned glass volumetric pipette. However, sometimes we still need to utilize those glass micropipettes when we can. The way that I use this thing is that up here at the very top, again, it's going to kind of zoom out on you, but there is a meter. You can kind of see that meter right there. I'll take a picture of it that will have a better focus on it. And I'm going to take the pipette and I'm going to dial in to the appropriate volume amount. The problem is that this only has room for 3 digits, and this goes up to a 1,000. So the problem is that when I do this, 1,000 is 4 digits, and this only has room for 3. So when this says 100, that is actually a 1,000. When this says 0, so the problem is that when I do this, 1,000 is 4 digits, and this only has room for 3. So when this says 100, that is actually a 1,000. When this says 080, that is actually 800 at that point. So that last digit is chopped off of the micropipette. These are our micropipette tips. I'm just going to open up the container. You can see all the tips that are ready to be loaded there. And I'm going to take the micropipette and I'm just going to literally push it down onto one of the tips and then bring this sucker up. And now you can see this is now loaded. I'm then going to put it into my sample, whether it's water or whether it's my unknown, and I'm going to slowly, up here at the very top, push the plunger down first, put it into my sample, and then slowly let the plunger off. In doing that, I'm ensuring that no air bubbles are getting inside the system. So you have to create the air pocket first, and then put it into your sample, and then slowly let up on the plunger at that point. And then to deliver the sample, I'll go to my container, and up here at the very top, I'll just push the plunger down to the first stopping point, and then there's an extra piece that you just push down even further. And that will send a little poof of air, so that way the remnants of the sample are going to be pushed out of the micropipette tip. All right, so there is the micropipette density setup. I'm going to take a few pictures of this process so that way you can see my measurements and see the readouts onto the balance. And then after that, you'll have the density part B finished for the lab experiment. All right, guys, so that's how we use a micropipette. So I know that you're not here actually doing that yourself, but they're pretty easy to use once you get the hang of it. And after I delivered that 1 milliliter of water to that container, this is the number on the balance that popped out on the readout, 0.9954. So this is the amount in gram that I am saying 1 milliliter of water measures. Now here's the issue. They give you a number that this should be in the lab, and they're telling you, hey, listen, just double check your number after this, and you're going to see that in the grade sheet. So if I use this micropipette the proper way, then that value should be pretty close to what they're telling me in the textbook. If I think that I used 1 milliliter, but I used the micropipette in a wrong way, and that's very common for people that do not have a lot of experience with the micropipette, then that amount might be a little off. So always double check my numbers, folks, because to be honest with you, sometimes I'm going to deliberately make mistakes, and maybe it was here, but maybe it wasn't, in order to see if I can catch you in understanding what the data means. Just because I'm doing it doesn't mean that everything that I'm doing is correct. So with the amounts for the sodium benzoate lab, with the amounts for this as far as the density lab goes, sometimes I could maybe deliberately mess up just to double check your math to make sure that you really do understand what the data is trying to tell you. Because folks, sometimes you'll come into the lab and you mess up. Sometimes you come in and you get it right. And this could be correct or it could be incorrect, as well as everything else that I will show you from this lab or in future labs. That's just the way that I work here. So I always double check you to make sure that you're paying attention. All right, so there's the volume of 1 milliliter of water, what I think is 1 mil, and there's the mass of that 1 milliliter. So see if that matches the expected table that you have on your end. Something else that I want to show you is that there are pretty major significant density tables for water at various temperatures. So the way that you'll read this particular table, typically they're always found in like the back of a general chemistry text. You can also find these online. But the very first column here is room temperature, and the second column here is fractions of room temperature. So for instance, if I was measuring the density of water at 10.5, well, I'd go down to 10, and then up here, there's 0.5. So I cross those two rows, or that column in the row, and I get 0.999654. So in a general chemistry class, they've lied to you. If you had an instructor that said the density of water is 1, that is false. That is phony. Nowhere on this table do you actually see 1, right? So it's close to 1, but they do 1 because it's pretty convenient. It's pretty easy to remember. However, room temperature is typically about 23 to 25 degrees. So 23 to 25 degrees, these are the rows that we want to focus on. And if you notice, this is further away from 1. We're getting 0.997s and 0.996s. So these are the values of the density of water. Your book in the procedure will reference 0.997. And you kind of know why they do that. Look, 23 degrees, 997.5, 25 degrees, 997, and typically room temp will always gravitate toward those couple of different temperatures. So 23, 24, and 25. So now you know where that number is really coming from. All right, so now that that water is taken care of, I moved on to the next part of the lab experiment. The next part of the lab experiment is going to have me take another empty container. So that's what I did here, a brand new one, nothing in it. I teared it out, and it's 0.0000, right? Okay, so after this, it then tells me to add amounts of liquid, which is the unknown, to that container, and then have me record masses as I begin to add or volumes to that container. All right, so here's my unknown. So we're going to call this UNKA. So this is my unknown A that I grabbed, and this unknown A is a liquid. It did have an odor to it. It didn't really have a fruity odor. It had a chemical odor that was associated with it, but it wasn't really fruity, but it was kind of that way. So sometimes in the observations, it's very difficult for us to maybe describe what we smell, especially, but sometimes describe what we see. But in this case, that's pretty easy. This was a clear liquid. There was no color, colorless. And it was pretty uniform, miscible. There was nothing in it that was floating around, no particulates or anything. It did have an odor. It was a chemical odor. It smelled kind of fruity, but that's about as far as I want to say about it. All right. So there's unknown A, and I put my micropipette tip into that unknown A, and I decided to suck out an appropriate amount of volume for it. Well, how much volume did I begin to suck out? This dial said 0 to 0. All right, so go back and take a look at my description when I talked about how to read the meter, but that is what my meter told me when I dialed it in and I sucked out that amount of liquid. All right, so 020 is what my meter read. All right, so I dispensed that into the container, and when I dispensed that into the container, my mass was 0.1750. So there's my first measurement. My first measurement probably did not match what the textbook told me to do. I just did whatever I wanted to do. It told me to measure out specific amounts of volumes. I said, bull, whatever. I'll just do what I want to do as far as volume. It's the same process, though, but I've got the freedom and the flexibility to kind of do that, and my data will still make sense. So there's my first addition, and my first addition is 0.2 mils. All right, so then I did it again, and I put another 0.2 mils in. So you got to kind of add those together to get a total volume. And the total at that point, which was 0.4, was 0.3461 gram. All right, then I did it again. I added another 0.2 mils. So now 0.2 and 0.2, and now my third 0.2 is 0.6. So 0.6 mils has a mass of 0.5179. Then I did that addition one more time. Again, another 0.2 gets added into the mix. So that's 0.2, 0.2, 0.2, 0.2. That gives me a total of 0.8. And that gave me a mass of 0.7242. Next, I did another 0.2 mil addition. That was 0.2, 0.2, 0.2, 0.2, 0.2, 5 of them. That gives me a total of 1 mil. And that 1 mil total was 0.9039. All right, so there's the data that I obtained from Part B. Now, on the grade sheet, what you're going to find are a couple of different calculations. And the first one, it's going to say, well, what was the density of 1 mil of that unknown? Well, I'm going to go back to this screen here, because this was a total of 1 milliliter here, because this was my fifth 0.2 addition, which is a total of 1. And that 1 mil is 0.9039. All right, so when I calculate density, density is grams per mil, mass divided by volume. So I've got gram from the pitcher, and I have milliliter because I know that I added 1 mil of stuff to it. Well, that means whatever my gram was divided by 1, well, that number is what the density is going to be. So that's going to be a very easy calculation for me, right? There's my mass. That mass is in reference to 1 milliliter in total. So that mass divided by 1 is going to be the density. And my density is already calculated for me. All right, next, it says plot a graph with grams on the y-axis and milliliters on the x-axis, slope and regression coefficient. I'll talk about this in just a second. The next one is probably going to say, calculate the density after each one of your additions. All right, so let's go back to this very first one. This very first one, this was my first 0.2 addition here. So my gram, 0.1750, divided by my volume, which was 0.2 milliliters. And I can use those two numbers and calculate density. What is that number? That's for you to figure out. Well, if I do it here, this was my next addition, right? So this was 0.3461, and this was in reference to 0.4 mils in total. This was my second addition, 0.2, 0.2. So calculate it. What's the density? Mass number next, 0.5179. And this was in reference to my third 0.2 addition. So 0.2, 0.2, 0.2. That was 0.6. And then you'll do the same thing here. And this is in reference to 0.8. So when you get to that part of the calculations, when it says calculate the density after each addition, that is what you'll do. Then it's going to talk about something about standard deviation. I'll talk about that when I talk about the Excel spreadsheet up here at the very top. And then it's also going to mention a density meter. Well, I made a mistake in the lab. I didn't use a density meter. We have one. We have an instrument that you can put a liquid in, and that liquid will automatically calculate the density for you. Okay, well, I could have used this, and I should have used it, but I just forgot to use it. So in your laboratory notebook, you're going to say, no density meter was used. And then the ID from the unknown list. In the lab packet, you're going to have a couple of possibilities that this unknown could be. So all of those you're going to have to look up the densities for. And then you have the density from this unknown that we did together, and you will match that density to the list of unknowns that it possibly could be, and which one will the unknown match with the best. And that's how you'll ID the unknown from that particular list. Now I want to go back up and I want to talk about this plot. The lab directions are going to tell you to make a plot, and folks, I'm not going to tell you to whip out a graph paper. Graph paper's for elementary school. We don't need graph paper here. We've got other things that are graph paper, and that's called Excel. So here is the Excel software, and as a student at Cape Fear, you have access to a free copy of Microsoft Excel if you don't have one. You just have to go into My CFCC and you go in to the Office 365 and you can use the online version for free, or you can download the software package onto your computer, and that way you can use it offline if you have to, and you can install it on your computer or your tablet. So the directions are going to tell you to make a graph. And in those directions, it's going to tell you a proper way to make the graph with. All right, so look at the way we did density here. Density is gram over mil. All right, well, in a graph, we often say rise over run is equal to the slope of a line. So maybe if you took algebra, maybe if you took pre-calculus, you were graphing line systems, you were plotting data, you were connecting the dots together to draw the best fit line. And we often said that you can calculate slope, and the way you calculate slope is take 2 points on that line and calculate the rise, which means how far up and down, and calculate the run, which is how far left and right. All right, so here is the graph, and normally a line would maybe come out to be like that. And we would take a point here, and we would take a point there, and we would look at those coordinate values. And we would take those coordinates, and we would subtract and look at how far it rises up to get to that point, and then how far does it go over to get to that point. And that's what we call the slope. We'll look at density. Density is very similar to this, right? Density equals gram over mil. Slope equals rise over run. So if we form this graph the proper way, we could use the graph in order to calculate the density for us just by simply looking at the slope of the line. Okay, so how do we do this? If you read the directions, it's going to tell you how to do it. Gram is on top, therefore that is in reference to our rise, which is the y-axis. So we want to plot grams on the y-axis here. And then milliliter is on the bottom. That represents the run, and the run is the x-axis, how far across, and that is the x-axis that goes this way. So we need to plot milliliters cumulative on the bottom. Well, what I did was 0.2, and then it was a total of 0.4, and then a total of 0.6, and then a total of 0.8, and then a total of 1. And then I had a gram associated with each one of those. So I need to make a chart. And I get Excel to do the work for me. So I'm just going to make up a couple of numbers here. Let's say that I did 1 mil, and then I did another, which brings my total to 2, and then another, which brings my total to 3, and another, which brings my total to 4, and another, which brings my total to 5. Okay, that's not what we did in our lab experiment. I'm going to let you plot the correct values there, but this is just an example. Next, each one of those we had a mass for. Let's say that that 1 mil addition was 0.5. I'm just going to keep it easy for you, 0.5. And then I added another mil to bring me a total of 2, and that weighed 1. And then the next addition weighed 1.5, and the next one weighed 2, and the next one weighed 2.5. Again, I'm keeping it easy. How do we use this data to make a graph in Excel, which makes my life a little bit quicker, a little bit easier because I'm using technology to my advantage? Well, here's how you do it if you've never used Excel before. So after I key in what goes on my x-axis, which is mils, and my y-axis in the next column, which is gram, I'm then going to click and I'm going to highlight the data. When I do this, Excel understands that it needs to keep the set of data together. And then up here at the very top, I'm going to see Insert. So I'll click it. And then in the center of the screen, I'm going to see a couple of different graphs, chart options, and we use just the dots. We don't like it when Excel forces a line to go through everything because we know data is not perfect. It shouldn't go through everything. So in the beginning, the only thing that I want is it to plot the data points. No line at this point at all. So I'm going to click that particular type of chart. And there's a couple of options. If you click this arrow that's right beside of it, do you want dots? Do you want dots with a line that goes through everything? Do you just want the line that goes through everything? Do you want a non-smooth line that goes through everything with the dots? Or do you want a non-smooth line without the dots? Folks, we just want dots here. We want to keep it simple. So I'm only going to plot the dots and that's it. And that's what we call a scatter plot. So I click it and my graph comes into the picture. And there is my graph. It looks like it's going to form a line, which is a very good sign that I did a pretty good job maybe with the measurements. All right, but this doesn't tell me anything yet. So I need slope. I need slope of this line because if I get slope, that's going to give me my density. And in addition to that, it's going to ask a couple of things. It's going to want to know slope and something that we call regression coefficient. All right, so what is all of that mess? Well, here's how you do it. Click on a data point. It doesn't really matter which one you do. Just click on one of them and all the data will get highlighted. And then when you're over one of those data points, you're going to right click with your mouse. Right click. And then you're going to go to this thing that says Add Trend Line. This is a line that doesn't go through all the points, but it will go through as many as possible, but it will make sure that it will stay a straight line when it does. Okay? This is what we like to use in a laboratory field. We know that data is not perfect. We know that you're not perfect. So Add Trend Line will draw a line and it will try to go through as many points as possible with the assumption that it might not can go through everything, and that's okay for us. So we're going to click Add Trend Line. All right, so when we do this, a box will show up over here on the right-hand side of your screen. You want to make sure that it's linear. There you go. And then I'm going to scroll down that box. Let me pull it back up again. I'm going to go down, pull it back up a little bit. And here at the very bottom, you're going to see an option that says Display Equation on the chart. Well, we need that equation. That slope is going to be my density value. So I'm going to hit check. And then it says display the R squared value on the chart. Well, I want that too. because in the lab directions, it's going to tell me to provide the linear coefficient number. And that's what that is. It's called R squared in Excel. This tells me how good of a line that I have just made. So I'm going to click that box as well. Then I'm going to bring back my graph so that way you can see it. And now this equation and an R squared value shows up on my graph at this point. If this was my density example, my density is the slope, and the slope is the number that is attached to my x. So in this case, the slope is 0.5, therefore my density is 0.5. The R squared number is how good of a line that I made, which means how good of a data did I present. 1 is perfect. And again, folks, I just made up these numbers. So in a lab, maybe what you would get here would be something like maybe 0.4893 or 4, and maybe 0.9987, and maybe 1.5019 or 18, and maybe 2.0991, and maybe 2.345 or 85. There we go. So you would actually get a bigger equation here that has a y-intercept on it now. But the slope is still the number that's assigned to the x. And that slope in this case is 0.4819, which means that my density is 0.4819 based on the graph. My R squared value, 0.9877, it's lower than 1. It's further away from it, which means it's not as good of a line as it could be. It's slightly imperfect, and we can actually visually see that. Look at the dotted line that it's drawn. And this point is a little bit above that dotted line, which means that that is my problem area. That means that maybe when I did this data measurement in a laboratory, something here went off. And that dot seems a little bit elevated, which means I could maybe go back and try this one again if I want better data. And this one looks a little bit lower. So maybe there was a problem with that one as well, and I need to go back and I need to redo that one to see if I can maybe get it to match up a little bit better on that line. So this is how we use Excel in order to generate a graph. And the graph in this case is a density graph. And the density graph will automatically calculate density for you if you look at the slope, as long as you plot the axis the proper way. So volume on the x, cumulative volume, and then gram on the y-axis. And that is how you need to plot this type of data in order to calculate density. Finally, next is standard deviation. Okay, so what is standard deviation? For those of you that have never provided standard deviation in a laboratory before, standard deviation is a way that we can look at how close the data is together. So what we're going to have here is going to be multiple density measurements, because we added 0.2, then we added another 0.2, then another 0.2, then another 0.2, and we calculated density for each one of them, right? So each one of those numbers might be slightly different. You know, in a general chemistry class, they normally give you the image of a dartboard. And they say you throw darts at a dartboard, and if all the darts go close together, you've got really good precision. Folks, that's another word to say standard deviation. If all of your darts are close together, you have good precision. If all of your lab data is close together where it needs to be, then you have very low standard deviation, which is very good. The lower the number, the better off this is going to be. So standard deviation in Excel is this code. Do not calculate this by hand. That's a waste of time. Why would you do it? You got technology at your fingertips. So use Excel for its purpose and allow it to calculate the standard deviation for you. So if I do these density measurements, and let's say I get 0.4895, 0.4888, 0.4904, 0.5101. That one seemed kind of off a little bit, right? And then 0.4811. How do I get standard deviation? Go to any cell. It doesn't really matter. Wherever you want the number, I don't really care. Go and click on that cell and start off with an equal sign. That equal sign means Excel wants to do a calculation for you. What kind of calculation do you want Excel to do? Well, you type in STDEV. That stands for standard deviation. It even tells me that. Calculate standard deviation based on the entire population. So calculate STDEV. You don't need anything else other than that. Then you're going to open your parentheses up. And now notice what it says. Number 1, number 2, number 3, and so forth. You can type these in, but why would you do it? Again, use technology to your advantage. You don't want to manually type in those numbers. The only thing that you want to do is click and highlight the set of data that you want it to do the standard deviation for. That's all that you got to do. Just highlight the numbers. And then finally, we have to put the parentheses back on the end. We have to cap it off. So that's what I'll do. And then when you do that, you hit enter. Ta-da! You've just calculated standard deviation. See how easy that was? You would make a math instructor insane with this, because all of the stuff that they talk about with standard deviation, they make you do it by hand. You know, take the average, take the data point minus the average, square it, plus the data point minus the average, square it, plus the next data point minus the average, square it, and then you take the square root of all of the sum of all of those additions. Whatever. Nobody needs to do that. Excel has it built in. Your calculators have it built in, folks. If you've got a TI-83, 84, or a fancier calculator, it's got standard deviation built in with it. Nobody needs to go through all that mess. And this isn't a math class. I know it might sound like one right now, but it's not. So I'm kind of testing your general knowledge about density, not how you calculate standard deviation. So get Excel to do it for you. At any point in time, if you have to do average, I'll give you another key. Start off with equal. There you go. Type in the word average. Open your parentheses. What do you want the average of? Highlight the data. Cap it off with the other parentheses. And then hit enter. There you go. It's even calculated the average for you automatically as well. So folks, use Excel, get comfortable with it. It is a powerhouse when it concerns calculations. I'm just showing you 2 of the hundreds and hundreds of what it can do. So these are the 2 most common types of calculations that we do in a laboratory. That is average and that is standard deviation. And now you know how to do it. All right, so you'll be making your own density graph with the data that we've obtained in the lab. That's not this data. Go back and take a look at the presentation to get that data off. And now you know how to calculate the standard deviation from the grade sheet. That's what it talks about. You now know how to do that. All right. Okay, so that's where this part of the laboratory is going to stop. That's all of the data that's associated with the density of part B. And I think that will give you enough to finish out the lab and kind of truck on and get your laboratory notebook together. You're also going to see another video. I'm going to focus on just the grade sheet in that one. This is probably the first time that you will be handwriting a laboratory experiment in a notebook with me. And I like to do the grade sheets to kind of tell you and give you some insight on what you should be writing down, what kind of statements need to be included, and so forth, and give you some general guidelines of laboratory notebooks as well. So that's what you're going to see in a separate video. If you've got questions about the grade sheets, that's where you're going to find those. And then, of course, you can also email me too at the same time. But this is going to have a third part. It will be one of the few times that I will do it, because once you see one grade sheet, the rest of them will work the same. But I at least want to take some time and talk about the very first one that you're going to be working on.